Hello, my name is Abdulmanaf Poonawala, and we'll be looking at the one-dimensional CNN approach for ECG arrhythmia analysis in a fog cloud environment. Now, when we come to the introduction, we already know that cardiovascular diseases cause a high number of deaths annually, making remote cardiac patient monitoring essential. We already know that with the rise in cardiovascular diseases, as well as heart rate failures, as well as heart attacks, we due to various lifestyle choices such as a more sedentary lifestyle, as well as inclusion of fast food, as well as other out of control habits such as pollution, etc., we know that something has to be done to help monitor our heart rate. So ECG signals that are normally monitored at a remote location can now be monitored in non-invasively with IoT devices like smartwatches and Fitbits while on the move. So edge computing and sensor-centric approaches have limitations due to their resource constraints. However, AI-based machine learning and deep learning models are still effective in disease analysis and classification. So we have new and developing products such as smartwatches, as well as mobile applications that are in connection with devices that help monitor your ECG levels at any time without needing expensive machines for it. So a proposed modular 1D CNN approach for the ECG analysis can ensure optimized delay in actuating emergency services during remote cardiac patient monitoring. So other related work that's done with regard to this, and what our paper is based off of, is that fog-based IoT systems are used for ECG analysis with various services, including data storage, processing, analysis, fault detection, interoperability, and security. Different systems use different architectures and algorithms for the ECG analysis, including discrete wavelet transformation, collaborative machine learning, and deep learning. Now, some systems use low-cost embedded boards and energy-efficient wearables sensors for real-time monitoring. Accuracy of ECG analysis varies based on the complexity of the methods employed. So on top, we also see a certain architecture such as the sensor layer, the fog layer, and the cloud layer all interacting with each other. Now, our proposed method also, so this is already a cloud computing approach, right? However, our method helps make this more efficient. We'll see how. So in the proposed remote patient monitoring system, we have a three-layer architecture, which consists of a sensor layer, a fog layer, and a cloud layer. Now, on our right, we can also see a 1D convolution neural network architecture that we're using. So we have an input layer, which goes through its batch normalization, the 1D convolution layer, an activation layer, as well as a max pooling layer. Now, this again goes through a 1D convolution layer, activation layer, and max pooling layer, which finally gets into a flattened layer, a fully connected layer, and then it comes out to the output layer as well as a softmax layer. Now, out of the three, the first we have is the sensor layer. So the layer consists of wearable IoT devices that collect ECG signals of cardiac patients, be it smartwatches as discussed before, or an entirely new device altogether. Now, these devices perform the sensing operation in a consistent manner and transmit the ECG signals to the fog computing nodes instantly located at the fog layer. So the sensor layer also incorporates actuators, including the alert systems and ambulance service that receive commands from the fog layer and function as per the outcome of the ECG signal analysis operations. Next, after the sensor layer, we come to the fog layer. And in this layer, it basically consists of a cluster of fog nodes that perform local data storage, data filtering, and data analysis operations. The local data storage ensures the faster processing of patients' ECG signals. And when the processing of ECG signals cannot be conducted by the fog nodes due to overhead, these data are forwarded to the cloud in a prioritized order for further processing. So the fog nodes also apply complex and robust data filtering techniques on the signals to eliminate noise and unnecessary complete data. And the inference model of the proposed ML model is executed at the fog layer, which classifies the signals and detects the abnormal case of the patient. Now, when we look at the results that we've achieved, right? So that in the database overview, we see that the study conducted performance evaluation experiments using the MIT BIS database, which had 48 ECG records of 46 individuals divided into 6 groups according to the AMI standard. All right. So the signal is segmented into heartbeats according to the PQRST sequence, which has a total of 42,021 ECG heartbeat segments of length 319 ms. Right. So the database is also divided into training, validation, and test subsets for the experiments, and the cross-validation method was applied to avoid overfitting and improve the model generalization. So it was trained using the 1D CNN model. The validation dataset was used for tuning hyperparameters, and the testing dataset was used to evaluate the final tuned model scale on unseen data. And the k-fold cross-validation method was used, and the mean of the model skill scores was summarized from the cross-validation runs. So this is basically a graph representation of what we talked about earlier with the data represented in a graph in 6 segments as discussed. So we have the beat groups and samples with a normal, left bundle, a right bundle, atrial, premature, ventricular, and paced with a total of 42,021. On the right, we can see the graphs of each of these, their heartbeats as well as the MS is recorded. Now, experiment results, right? So after the study was conducted, we use hyperparameter tuning for the grid search CV algorithm, as well as the model that we used was the 1D CNN, right? So the model achieved a 99.46% accuracy with a batch size of 64, a learning rate of 10 to minus 3, and Adam optimizer after 44 epochs. So the model was trained with only 2 1D convolution layers, which contributes to its fast learning speed. And the proposed model outperformed existing models evaluated on the same dataset and reached promising results with limited epochs. Right? So the proposed model showed a higher accuracy with the average area under the curve rate close to 1. This is a data representation of what our model achieved, with figure 6 showing the training and validation losses per epoch. As you can see, it does get lower and lower. And figure 5 showing the training and validation accuracy per epoch. As you can see, there's a sharp increase with the validation bringing the accuracy down as it should to avoid overfitting. The performance measures on each segment are also given on the bottom left, as well as the hyperparameter tuning we've done on the bottom right. On the bottom left, you can also see our recall F1 scores as well as the precision for each of them individually. Now, we come to the crux of our paper, right? So the efficiency of the hybrid fog cloud infrastructure. So what we've achieved is essentially we've also tested this using a Raspberry Pi 4 devices used for the fog environment and Google Colab's Tesla K80 used for the cloud environment. So when we've done this and compared it to 2 existing approach, one is the IoT cloud and one is an IoT fog. It showed that the training and the execution of the training model on resource-constrained devices in the IoT fog incurred significant overhead, and executing the inference model on computationally enriched resources in IoT cloud resulted in less overall CPU utilization, but higher financial cost. So looking at these 2 problems, our approach sort of melded them in a way that eradicated the problems, right? So the proposed approach executes the training model in cloud and the inference module on the fog, resulting in less financial cost and improved response time compared to the IoT cloud. Overall, the proposed approach balances CPU usage and optimizes latency, resulting in less financial cost and improved response time. Thank you.